See, first of all, you have to understand certain terms, right? Now, what is that particular term? Just understand, right? Basically, what exactly happens, understand. When we have this particular beaker, we have this particular beaker, right? In this particular beaker, a particular reaction we are trying to bring about. Like, for example, I want to carry out a reaction between H2 gas and O2 gas to form H2O. That's my potential reaction. I want to carry out this particular reaction. Okay.
Yeah.
When I have to carry out this particular reaction, so what do? I close this beaker and I add H2 and I add O2 and I basically wait for them to collide, right? And I want these molecules of H2 and O2 to sort of collide. So these are, let's suppose the black ones are the O2 molecules, and let's suppose the blue ones are the H2 molecules, right?
Right.
And I want them to collide and I want them to form the water molecule. So what exactly is happening right here? Just understand. When I want them to collide, so one particle is moving here and one particle of the blue particle is moving here, O2, H2 particle. So black ones and the blue ones are trying to collide amongst each other. So one tries to
Right.
move here, one here, and they're colliding like this. They're colliding like this, right? When they're colliding, so I have told you this before as well, that we need the previous bonds, H and H. So I hope you're understanding that when we say H2, H is one electron, another H has another electron, and a bond is actually being formed between both of them. So the H2 molecule is formed, and on the similar lines, O's atomic number is 8. So configuration is 2, 6. So it has 1, 2, 3, 4, 5, 6. And another oxygens would be 1, 2, 3, 4, 5, 6. So when you sort of form the bond like this, and when you form the bond like this, so it would be O double bond O.
Right.
So the two reactant part, these reactants, they are colliding. Yes or no? These reactants are sort of colliding.
Yes.
But what exactly is happening? That H and O and double bond O, when they collide, when they collide like this. So basically O comes here and H comes here and they just collide. So there is a possibility that water is formed. So that collision in which old bonds sort of break, the dotted line between H and the dotted line between O and O basically shows that the bonds are breaking down. That H and H bond is breaking down and the O and O bond is breaking down. Do you understand? And thereby new bonds between H and O is being formed. We have done that. So we know that this is called as the activated complex. Do you remember that? In the collision theory, we did this. You understand? So when we have this particular structure being formed, but for this old bonds to break and new bonds to form. So what is a new bond right here? This is my new bond. So this is a new bond in formation, and this is the old bond which is in breaking. So the old bonds are breaking and the new bonds are being formed. So that is happening because the molecules, they have collided with a certain amount of energy. See, if the molecules are moving very slowly, so then the collision between these two molecules would not be so sufficient that the old bonds would be able to break down. So there is certain amount of, energy you need with the reactants to collide. So if I say that, this is the graph to represent what? That as the time progresses, so this is the energy of the reactant molecules. So this is the energy axis, which is my y-axis, and this is going to be my x-axis. I hope you're understanding. Yes or
Yes.
no?
Yeah.
So this is my energy of the reactant. So I'll say, okay, the energy is, let's suppose, 0. So the graph is something like this. So with 0, you have to provide it some energy from outside. Initially, we are assuming that there was 0 energy, and you have to provide some extra energy from outside. You understand? And this
Yes.
extra energy that you're providing from outside is actually called as the activation energy. So at this particular temperature, at this energy, the old bonds between H and O are breaking and the new bonds between O and O are actually being formed, are breaking, and the new bonds, these black dots are actually representing the new bonds.
Right.
These
Yeah.
bonds are being formed. So why this is happening? Because we have provided this much amount of activation energy. Because initially we are assuming that there was nothing, no energy with the reactants enough to
Yeah.
collide in such a way that old bonds could be broken down and new bonds could be formed. And now you have provided an extra activation energy from outside. How you have provided? You have provided that energy by heating. You have heated this mixture. And when you have
Right. Yeah.
heated this mixture, so these molecules will now start to collide. They will start to move faster. And when they start
Yes.
to move faster, what exactly happens? You tell me. When they start to move faster, there is a force of they hit to each other at a very fast pace. So when they're colliding at a fast speed, I hope you're understanding that the product so formed, yes or no? The product so formed will have the old bonds breaking and the new bonds being formed. And finally, the product shall be formed. And finally, the product shall be formed. So, generally, this graph that we have to draw is generally right from the starting of here. Generally, this graph is something like this to show that the product is actually being formed. So, this part with the so this blue part that I'm drawing is actually showing the product being formed. So, I hope you're understanding that this is one full curve. You understand? This is one full curve.
Yeah. Yeah.
Right? And when we have this one full curve, what exactly is happening? Just tell me. What exactly is happening? That this is showing that, ma'am, this is the energy of the reactants. This was the energy of the reactants. But at this energy of the reactants, the collision was not a, a energetic collision. And here, the temperature would rise. You have to give it activation energy. So that should be EA, right? That should be EA. And here
Right.
we reach, so this should be my threshold energy. This should be my
Okay.
threshold energy. And what is happening at the threshold energy? That energetic collisions are taking place. Energetic
Okay.
collisions are taking place. And when energetic collisions are taking place, what is happening? The old bonds are breaking. The old bonds are breaking. And new bonds are actually being formed. New bonds are formed, and thereby the final product. So this shall be my EP. That shall be my energy of the products. I hope you're understanding.
Yeah.
So when we have this particular graph that is being formed right here, I hope you're understanding that we need to provide. How should I write it down? That E reactant plus the activation energy will give me E threshold. And that is the threshold energy, is the minimum energy that the reactants must have in order to
Okay.
form the products, in order to have the
Right.
effective collisions. At threshold energy, effective collisions is maximum. Effective collisions is maximum. So I hope you're understanding that, at the threshold energy, the conversion of reactant to products is maximum. And that's when the speed of the reaction is maximum. I hope you're understanding.
Yeah.
So, when do we have the maximum conversion of reactants to products? When we have enough threshold energy, when we have effective collisions, when we have energetic collisions. When we have energetic collisions. Do you understand my point? So, when do you think we have energetic collisions? When the molecules have high temperature. So, what are we trying to tell here is that, we have three types of speeds. We have three types of speeds with the molecules. So understand. So let's suppose we have this group of people. Let's suppose we have this group of 10, 12, 15, 20 people. Yes or no? And I want all of these. So one person is really fat here. He's a fat person. And two people are very fat. One person is very lean. So these dotted people are very lean, very light. So the average people lie in this category. They're neither very lean neither very fat. And I want them to run from point A to point B. And I will say that the task is complete only when this group basically moves from end A to end B. Just listen to me very carefully. It's a very important topic. So I hope you're understanding that if the group of people is moving from end A to end B, I will consider the task to be complete only when all the members of the group reach from point A to point B, isn't it?
Right.
But what is happening? That these people, the people who are very lean, would reach from A to B in no time. Rather, hardly any time they would take. So these people are reacting very fast. These people are, completing my task at a very fast speed. But those people who are not either not very fast, who are lean, not very lean and not very fat, they might take 10 minutes to reach from point A to B. And the lean ones would take hardly 1 minute because they're very, very thin, very light, and they just run like at the speed of light, very fast. So
Yeah.
within 1 minute, they would reach from point A to one B. But the majority of the people are running with a certain speed such that they would take 10 minutes to reach from point A to point B, and then they would all reach here within 10 minutes. But these particles who are very, very fat, you know, they would take an hour to reach from A to B because they're very, very slow. Are you understanding? So,
Yeah.
what does that mean? What does that mean? So, there are particles who are moving with an average speed. So, this speed, let's suppose the speed of most of the particles in this beaker or the most of the people in this group was, let's say, 10 kilometers per hour. So, most of the people were running with 10 kilometers per hour. But these lean ones, they were running at the speed of 90 kilometers per hour. So, they just covered the distance like in no time. And these
Right.
people, they were traveling with 1 kilometer per hour, very slow, the heavy people. Yes or no? So
Yes.
that is actually the scenario of a beaker. So for example, if I have this particular beaker and if I have certain different molecules in it, isn't it? So few molecules are red molecules, some are the blue ones, some are the green ones, isn't it? Some are the yellow ones and so on. So
Yeah.
different molecules we have right here in the beaker. Some black molecules as well. Yes or no?
Right.
So all of these are representing nothing but the gas molecules. But why have I depicted them with different colors? So I am saying the red particles are actually moving with what? The red particles are moving with the speed. The blue particles are also moving with the speed. The yellow particles are also moving with the speed. The green particles and the black particles. They're all moving with a certain speed. So let's suppose the red particles are moving with the speed of, 2 meters per second. The black particles are moving with the speed of 10 meters per second. The green particles are moving at the speed of 1 meters per second. The yellow particles are moving at the speed of 3 meters per second. And the blue particles are moving at the speed of 4 meters per second.
Right.
So you tell me, by looking at the diagram, do you see that the maximum particles here are black particles? So the black particles that I've drawn right here in the diagram, I hope you're understanding that the black molecules are more in the beaker.
Yes.
And
Right.
these black molecules, which are more in the beaker, they are all moving with the speed of 10 meters per second. So I will call this speed as the most probable speed. What will I call the speed? I will call this speed as the most probable speed. Are you understanding?
Yeah.
And when I call this speed as the most probable speed, what do you understand would this be? If I call the speed as the most probable speed, what do you think would this be? Tell me. If this is going to be the most probable speed, I hope you're understanding most probable means that this is the speed acquired by most of the molecules in the beaker. Are you understanding? This is the speed acquired by most of the molecules.
Right.
Most of the
Yeah.
molecules in the beaker move with the speed. In the beaker, move with this speed. So when most of the molecules actually move with the speed, what do you understand by this? That, ma'am, most of the molecules are moving with this speed. This is my most probable speed. Yes
Right.
or no?
Yeah.
And this is my maximum speed.
Yeah.
This is not exactly my maximum speed. This might be some value. But there are few particles, who are moving with, let's suppose, let me make this speed is not the maximum speed. Let me make this speed as somewhere around the 0.5 meters per second speed, or I would say the 2.5 meters per second speed.
Okay.
So
Right.
this speed is actually acquired by most of the molecules. So the number is more,
Right.
but the speed is not the maximum. But have a look at the speed here. The blue particles, the speed is 4 meters per second, a very, very high speed in comparison to all the molecules right here. In comparison to all the molecules right here. Are you understanding?
Right. Yeah.
4 meters per second, but that is being acquired just by the blue molecules. And as much as I can see, there are only 3 particles, blue particles in the beaker. That means this is the very high speed. So this such a very high speed is also called as a root mean square speed. The root mean square speed. You understand? And then
Yeah.
rest all of them, I would call them under the category of the average speed. So you understand that, when I am drawing this curve, that ma'am, when the molecules in a beaker are moving, so I will say that, at a certain temperature, what is this? This is delta n over n. Delta n over n means that if, for example, in this beaker, I have, let's suppose, 200 molecules. So 200 total molecules I have in this particular beaker.
Right. Yeah.
200 total molecules. So I would say 3 out of 200 are moving with the speed of 4 meters per second. Are you understanding? 3 particles.
Yeah.
Only 3 blue particles are there out of 200 which are moving with the speed of 4 meters per second. Understood or not?
Right.
Right? So yellow particles, what are these yellow particles? What are these yellow particles? These yellow particles might be, just count the yellow particles, 1, 2, 3, 4, 5, 6, 7, 8. So I will say 8 out of 200 are moving with the speed of 3 meters per second, isn't it?
Oh,
Count
okay. Yeah.
count the number of black particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. So let's suppose approximately 150 particles. So I will say 150 particles out of 200 are moving with a speed of 2.5 meters per second. So this is called fraction of molecules. This is called fraction of molecules. Are you understanding? So when we are
Yes.
talking about the fraction of molecules, what would that mean? When we are talking about the fraction of molecules, what do you think would mean? That when we are drawing this particular diagram right here, so delta n over n means fraction of molecules. So capital N represents here the total molecules. And delta n represents here few molecules out of the total molecules pertaining to a certain speed. Few molecules out of total molecules following a certain speed. Following a certain speed. That's how the fraction of molecules is formed. Right?
Right.
And this is the progress of the reaction, and this is the speed. Now, let's talk about this part. So, if I draw the graph acquires this bell shaped curve. This graph acquires this bell shaped curve. Now, what does this represent? Just understand. It represents that, ma'am, this speed, this particular speed, this speed is actually being acquired by these many particles, is actually being acquired by this particle, the red particles. That means, so obviously the particles would be somewhere here like this. That ma'am, 5 particles, 10 particles, 15 particles, isn't it?
Yeah. Right.
The particles would be something like this. So it would be 5 particles, 10 particles, 15 particles, 20 particles, and then 25 particles, and 30 particles, and 35 particles, and 40 particles, and 45 particles, and 50 particles, and 55 particles, isn't it? So what exactly is this representing? Just tell me. What exactly is this representing? That, ma'am, when we have this particular graph, so this value of speed is actually being acquired by maximum particles. 50 particles are actually acquiring, 50 particles out of the total particles are actually acquiring this speed. So can I say this is going to be my most probable speed, VMPS? VMPS means the most probable speed. Are you understanding?
Okay. Yeah. Got it.
So this would represent most probable. And the fastest speed was actually 2.5. was 4 meters per second, but that was being occupied by only the blue molecules. So can I understand that the molecules possessing the fastest speed is the very less? So where would that root mean square speed lie? So this graph here, the red line would represent the most probable speed. This would represent VRMS, sorry. Not the most probable, the root mean square speed. So you can understand from the graph that the molecules possessing the highest speed is very less. Only 25 particles out of 200 particles. You understand? So what
Right.
one understanding about this graph is that the peak of the graph. First of all, you'll say that this is going to acquire a bell shape curve.
Yeah.
Secondly, this acquires to tell you that the peak represents the most probable speed, the most probable speed, because that is the value of the speed which is actually acquired by 50 molecules out of the total molecules. Do you understand my point? Yes or no?
Yes.
All right.
Yeah.
Second part that you have to understand. Second part that you have to understand. Third part, that the molecules here you understand as the speed. See, because this is here, this is the speed axis. So 1 meter per second, 2 meter per second, 3 meter per second, 4 meter per second, and so on. The speed is increasing. So here the speed might be 20 meters per second, but the molecules which possess 20 meters per second is very low. You can see.
Right.
And the molecules which possess 1 meter per second, 2 meter per second to 1.5 is also very less. So how do you read this
Yeah.
graph? The molecules possessing, the molecules possessing, the molecules possessing very high speed, or very low speed are also very less. Low speed are also very less. So the most of the particles, undergoing a certain reaction are lying in which range? Are lying in this range where majority of the reactions would where majority of the molecules would react this kind of speed, the area between the two black lines, that is the area where most of the molecules are colliding, and most of the molecules are moving with a sufficiently larger speed. So
Yeah. Right.
I would say the molecules between the two black lines, the molecules between the two black lines under the curve represents represents what? Represents the maximum particles moving with this velocity. Particles moving in this velocity range. Moving in this velocity range. Yes or no? Moving in this
Yes.
velocity range. I hope you're understanding. Right? And
Yeah.
the fifth point about this graph shall be that the area under the graph gives you the total number of molecules. The
Yeah.
area under the graph gives the total number of molecules. Gives the total number of molecules. So the area under the graph gives the total number of molecules, right?
Right.
And now this was my Boltzmann postulates. So these are my Boltzmann curve. So I hope you're understanding that under this particular range, this range that I'm talking about, this shaded range,
Yeah.
this range, the yellow range. In
Yeah.
between these, whatever number of molecules are coming up, they will collide with such a speed that they will end up having an effective collision. And when they end up having an effective collision, they will end up converting it into products. Because here the speed is a sufficient speed. You understand? It is neither a thin speed, neither a less speed, neither a very fast speed. It's a sufficient speed so as to collide and convert the reactants into products. I hope you're understanding. Right?
Yeah. Got
Hmm?
it.
Now, what is happening? The point is, now the question is that this is happening at a certain temperature T1. The moment I increase the temperature, where will the curve shift? You understand? So the curve was something like this. The curve was something that in the x-axis we were representing velocity, and in the y-axis we were representing delta n over n. And this was actually my curve. The blue line was my curve. Now, the moment I increase the velocity, see, understand what is happening? At a certain temperature T1, these number of velocity was actually representing number of particles. Yes or no? So, this number of particles, the N1 particles, were possessing this V1 speed. But as the temperature increases, obviously the particle speed would increase. So, this curve will shift here. This curve will shift right here. So what does this mean? What does this mean? So the particles moving with this v1 speed would also decrease because their speed has actually increased, isn't it? These particles n1, which were actually moving with which speed? They were moving earlier with v1 speed. But
Right.
now what has happened? As you have increased the temperature, just understand, as you have increased the temperature, these n1 particles are now moving with v1 speed. These particles are now moving with the v1 speed, with this v2 speed. I hope you're understanding.
Yeah.
And the particles moving with the v1 speed have actually decreased now because their speed has increased. So I hope you're understanding these particles, which are actually this speed vn, was actually being acquired by these particles earlier.
Okay. Got it.
But now the same speed is acquired by these particles. Why? Because these particles' speed has actually increased. So they have now started to move where? They have actually started to move at a faster speed. Do you understand?
Yeah.
You understand? So these molecules, the number of molecules moving at this speed were earlier low at the blue point. But with this, so like suppose 100 molecules are moving with this speed now. And now what has happened? Those 100 molecules are actually moving with this Vn speed. They have now reached the most probable speed of the lower temperature. So this graph states what? This graph states that as you increase the temperature, as you increase the temperature, so we had delta n over n, and we had this velocity, and we had this earlier curve at temperature T1. At temperature T1.
Right.
And as you increase the temperature, the curve will go down and will flatten up. And this would be the area. This would be how it is going to be. So the area, so you understand that there is a fall. This area that has been decreased, and this decrease in area is actually being compensated here by the increase. The curve has shifted upwards also. So here the
Right.
curve has gone downwards, so here the curve has gone upwards. So the number of
Yeah.
particles, what does it say? It says it was temperature T1, it was temperature T2, and definitely temperature T2 was greater than temperature T1. And area under the curve has not changed. Why? The area under the curve has not changed. Why has the area under the curve not changed? The reason is that whatever is the decrease in the area because of the flattening of the curve is actually being because the flattening of the curve is actually being seen by whom, is actually being compensated by the increase in the area right here, is actually being compensated by the increase in the area here. You understand my point? So that is the concept. That is the concept. So we have delta n over n right here. We have the
Yeah.
velocity here. So I hope you're understanding that this velocity was actually being possessed. So these number of particles, let's suppose the 10 particles, they were earlier moving with this blue velocity. But the same number of particles are now actually moving with this red velocity, this green velocity, this one.
Okay.
So the
Right.
V2 velocity definitely would be greater than V1 velocity. So the temperature T2 is going to be at a higher temperature than temperature T1. Yes or no?
Yes.
Understood or not? So this is going to be the concept. This is going to be the concept. So this is my Boltzmann curve. So now I hope you're understanding the moment you increase the temperature. Earlier, what was the range of the occurring of the reaction? This was the range. This was the range. This was the yellow range. And now the same range has now shifted here. That the same range actually occurring in this particular region, is actually occurring in this blue region now. Do you understand?
So yeah, so we can say that the number of particles have basically increased,
The number of
right?
particles undergoing collision have increased, definitely. And you're also say that, see, understand, it is going to be now more broader area. So
Right,
more particles are undergoing more effective collision, so more product is being formed. And here the
right.
area hit was this yellow area. Are you understanding? So this yellow area
Yeah,
would basically had less number of molecules, and obviously the collisions was also less effective because they were happening at a lower velocity. The blue
right,
area lies in that region where there is more velocity. The higher velocity region is this. So more effective collisions would take place here. So a line is actually stated. It says, as we increase the temperature, as we increase the temperature of a reaction, as we increase the temperature of a reaction by 10 degrees, the rate of the reaction doubles. The rate of the reaction doubles. Do you understand? The rate of the reaction doubles. Yes or no?
yes,
Right?
understood.
So this is going to be my Boltzmann curve. Understood or not?
Yeah,
Right? That is the answer. Understood or not? Tell me.
yeah, got it.
All right. So this is the chapter. Now, if there is anything that is left, you can let me know. And I think this is it for today's class.